Yes, I wanted to briefly describe how to use the diamond lattice to calculate um, energies for substituted cyclohexanes, looking at 1617 interactions. Secondly, I also want to show how one should be very careful to look at 1,3-diaxial interactions. So here's an example. I'll put on the diamond lattice of cyclohexane. The chair is indicated in shaded blue. And I haven't put all the hydrogens on, but I'm sure you can imagine where they go. But on this position here, I put a methyl group with the C and 3 H's. Now, this is axial, so it's clear that there's going to be some steric interactions they have to deal with. And specifically, look at the other axial hydrogens on the ring that are pointed in the same direction. Clearly there's one here, and there's one here. The blue represent hydrogens on the ring. So if we look at them, we can easily see that if we start with this hydrogen here, there is a 1, 2, 3, 4, 5, 6 atom interaction, and likewise there'd be one in the other direction too. So let's count that out. Only this time we'll start over here. So if we'll label that hydrogen 1, 2, 3, 4, 5, 6, what we see is that essentially there's a 6-atom interaction here. Okay. So hopefully this makes sense. And notice that if you look at this really carefully, this sort of completes a 6-membered ring. If you look at essentially the placement of this hydrogen and this carbon 6. There's also one other one, and that's listed here. And of course, this clearly shows, again, if we were to count from here, 1, 2, 3, 4, 5, 6, and again, 6-atom interaction. Notice that hydrogen and that hydrogen here, if one drew a line there, would complete this ring. So anyway, I think the 1,6-diaxial interactions are really pretty apparent. But let's go back for a second. Without bother counting the atoms, we should always be aware of the potential for 1,3-diaxial interactions, because if you look at where this methyl group is positioned, and this hydrogen, they're both axial. If this would be considered this carbon 1, 2, 3, that they're 1,3 away. The substituents, well, this substituent, the methyl group, is 1,3 away from this axial hydrogen. Likewise, if you count this as 1, 2, 3, this methyl group is 1,3 with respect to this axial substituent. And of course, it is those hydrogens that will interact with this methyl hydrogen to produce the 1,6-atom interactions. So whenever you're looking at a substituted cyclohexane ring, in which you have, especially when you have an axial substituent, you will always have basically 1,3-diaxial interactions that you must look for. And I think you should be perfectly aware too that if the methyl group was pointed down here, and of course you can imagine I'd have, this is the carbon, I'd have an H here and an H here and an H coming out here parallel to this. Okay. What we would have here is another potential 1,6 interaction with this particular hydrogen coming down. So again, if I have an axial group coming down here, it would be 1, 2, 3. There would be a 1,3-diaxial interaction with this particular hydrogen coming down, or a 1, 2, 3. 1,3-diaxial interaction with this hydrogen coming down. So whether the axial group is pointed up or the axial group is pointed down, always look, if you have an axial group on one face of the ring, for 1,3 interactions with the hydrogens on the ring. And that obviously occurs whether the substituent is pointing up or down, because there's always going to be axial hydrogens pointing down 1,3 away from them. And of course, all those, at least in the present example with the methyl group, would be 1,3-diaxial interactions and 1,6-atom interactions, each costing 1 kcal per mole.